All right, so now we're going to work this t-test. So the formula for the t-test is x bar minus mu over s sub x bar. She gave us in the scenario mu for the general population. Let's put that down there so we remember. That's the general population goes out on average 10 times a week before the coronavirus. We know that we got a sample of 4 scores of people who went out, the number of times people went out after the coronavirus. And now we need to figure out all the other information that we need. The t-test says we need x bar, so we're going to have to figure out the average from these scores. The t-test says we need s sub x bar, so we're going to have to figure out the standard error of the mean from these scores. The standard error of the mean is just the standard deviation. Remember that the standard deviation is how spread out the scores are, divided by the square root of n. The standard error is the standard deviation divided by the square root of n, and the standard deviation is just the square root of the sum of squares over n minus 1. Remember that n minus 1 is degrees of freedom. Okay, a sum of squares, we're going to square all the x's, add them up. We're going to add all the x's and square them and divide by n. So we've got a little bit of work to do, but not so bad, and I'm going to work through it with you so we can make sure we get to the right answer. So I think here's what's missing. We need a sample mean from the corona, people who are staying in because of the corona. We need s sub x bar, and in order to get s sub x bar, we need s. So we need to figure out all of this. And the mean seems like it's the simplest. It's just an average. We add up all the scores, divide by n. So let's do that. So when we add up all the scores, I get 3, 4, 5, 6, 7, 8 divided by 4, and I get 2, and that's the average of the scores. So we're going to plug that in right here. That's the average of the scores. Now we need to work on the standard error for the formula. So the standard error requires that we compute s, and s requires that we compute a sum of squares. So let's work on the sum of squares. So over here, let's put x squared. We're going to square all the x's because order of operations says if you don't see any parentheses around anything, then you do squaring first before summing. And so we're going to square all these x's. So we got 4, 9, 1, 4. And then we're going to add them up. And I get 18. So over here in the sum of squares right here, it looks like we have 18, which is the sum of x squared. Now we've already added up all the scores when we computed the mean. We added them up and we found that the sum of the scores was 8. So 8 squared divided by, and we have 4 scores over there, so 4. So I get 18 minus 64 divided by 4. And 64 divided by 4 is 16. So I get 18 minus 16. So I get 2. The sum of squares is equal to 2. So now we move from this formula. Now we have a sum of squares so we can plug in. So 2 divided by 4 minus 1. So 2, this is the square root of 2 divided by 4 minus 1. So I get the square root of 2 divided by 3. And I need a calculator for that. So let's look at our calculator. So I get 2 divided by 3, and then take the square root of that, and I get 0.8165. So 0.8165, that's what I'm getting. So this is equal to 0.8165, and that's S. Okay, so S is 0.8165. And then S sub x bar, the standard error, which is in the formula right here. So how spread out are the means? This is how spread out are the raw scores. This is how spread out are the means. The means are spread out, S divided by the square root of n. Remember, we got that from the central limit theorem. The central limit theorem says that the means are n times less variable than the raw scores, and the standard deviation of the means is the square root of n times less than the standard deviation of the raw scores. So let's compute that. So S sub x bar is 0.8165. 0.8165 divided by the square root of 4. So 0.8165 divided by 2. So let's get back to our calculator. So 0.8165 divided by 2. And I get 0.41. And let's round to 2 because we're done with the problem. So I get 0.41, so 0.41. And now we can get up in there and solve for t because we have everything we need to solve for t. So let's get rid of this right here. And t is equal to x bar, which is 2. I got it from right here, 2, minus 10 divided by the variability of the means, the standard error of the means. We got that right where? 0.41. So 2 minus 10 is minus 8 over 0.41. So t is equal to, let's figure it out, 8 over 0.41, 8 over 0.41. T is equal to 19.51. So let's see, 19.51. All right, so now we have t, 19. So how spread out are our means compared to how spread out they ought to be just because of random normal variation in the sampling distribution when the null hypothesis is true? If there's nothing going on between these two means, they ought to be spread out this far. How far should they be spread out? That's this. How far are they spread out? That's this. And the ratio is 19.51. They're 19.51 times more spread out than they ought to be just due to sampling distribution, just due to the sampling distribution of the mean, just natural normal variation sampling error. Okay, so then this is how far they are spread out and how much further they're spread out than they ought to be due to sampling error. And we need to compare that to a critical value. Now where we are right now is we need to test the null and reject or fail to reject the null. So our t was 19.51. And what's our critical value for t? And actually that was a negative, but that doesn't so much matter. What we need to do, if this is a test of differences, it doesn't matter whether it's a negative difference or a positive difference. Any difference more than the critical value is going to be significant. So we need to compare 19.51 to the critical value. Remember, the critical value is this area over here in the tail, the critical value, beyond which is the region of rejection. And if our t value falls into this region, we reject the null hypothesis. If it falls into this region, because it's a two-tailed test, if it falls into this region of non-rejection, we fail to reject the null hypothesis. So here's the region of non-rejection, here's the region of rejection. We have a two-tailed test because we had a non-directional hypothesis, equal and not equal. So we need to look up t critical. So I printed out the t chart, and in this t chart it says, which are you doing, a one-tailed test or a two-tailed test? Well, we're doing a two-tailed test. And in a two-tailed test, if we use alpha 0.05, the t distribution is based on degrees of freedom, not sample size, but degrees of freedom. So we have 4 participants, 3 degrees of freedom. We're using alpha 0.05. It's a two-tailed test, so you just find it in there. And it looks to me like on 3 degrees of freedom, the two-tailed test, alpha 0.05, our critical value is plus or minus 3.182. So let's go back over here. So this is 3.182, and this is minus 3.182. So this value needs to be bigger than 3.182 in order to reject the null. And 19 is bigger than 3.182. See, if these means were just drawn at random and they both came from a sampling distribution where mu is 10, then they would be 3.182 standard errors away from one another or less just by chance. but they're 19 standard errors away from one another. And so T critical is 3.182, but 19 is way more than 3.182. So we're going to reject the null hypothesis. And remember, the null hypothesis was that these means, mu for the general pop and mu for corona time, they were the same. And we have to reject that in favor of the alternative hypothesis that they're not the same. And then we need to state conclusions. And the conclusion is that there's a significant difference in the number of times we're going out now versus in the general population a year ago. There's a significant difference. And it looks to me like we're staying home more. Look at the means. So now we're going out 2 times. Before we were going out 10 times a week. We're staying home more now since coronavirus. T-test. Click.